I'm Martien den Hertog, and I will present our work about in-situ transmission electron microscopy, biasing and heating experiments of semiconducting nanowires for correlated studies and electrical contact formation. And I just wanted to add that no, I will not yet show this result about the single charge detection, but sorry. So this work is performed at the Institut Nel in Grenoble with a strong collaboration with CE Grenoble and also researchers in the Paris region and in Technical University of Vienna. So because Christian told me it's very many different subjects in your lab, I made a very basic, this first basic introduction. So the material I'm going to speak about today is semiconductors. And as you know, in metals, we have very easy and good conduction. Well, in insulators, we have this large band gap, so it's very difficult for a current to flow. And basically, semiconductors are in the middle and they have a band gap, but it's not so big. And interestingly, we can tailor their properties with doping, and often they are sensitive to light. So with light, we also change their conductive behavior. So semiconductors is the first ingredient of my talk. And the second ingredient is nanowires. And semiconducting nanowires are highly studied today because they are very promising for many different device applications. For example, field effect transistors or light emitting diodes or solar cells. But of course, there are some challenges remaining for successful implication of these nano objects in devices. And among these challenges, we can first have a variability issue, that every nanowire can be slightly different even though it is grown or fabricated under nominally identical conditions. And to better understand this problem, it can be interesting to study the same structure with different techniques to make a correlation between its properties and its crystal structure or chemistry at the level of the same unique object. For all these device applications, we also need electrical contacts to the nanowires, and therefore it's very important that we can fabricate and control high-quality electrical contacts. And finally, in all these devices, we need some gradient of potential landscape or potential barrier. And these are highly influenced or made by doping and surface charges of these objects. And so to truly understand their functioning, it's very interesting to study the electrostatic potential at nanometer length scales. So basically, I will talk about all these three challenges today. Bringing me to the outline of my talk, first I will explain some words about the sample fabrication that we used and about the transmission electron microscopy technique that was employed, and then show you three different studies. First, this is a correlated study on gallium nitride, aluminum nitride nanowire heterostructures. Then I will show you some results where we make aluminum contacts on germanium nanowires using in-situ metal propagation. And finally, we study a Schottky contact on a zinc oxide nanowire using in-situ biasing and holography. So here you see basically the working horse sample structure of all these experiments. So we are working on a silicon nitride membrane that can be planar or with a hole. And on top of this, we have a nanowire, a semiconducting nanowire that is contacted with electrical contacts. And this kind of structure allows to do a multitude of experiments on the same object. So we could hit it with photons or electrons, study different signals coming out, or the transport characteristics of the nanowire. And all this can be combined with transmission electron microscopy based techniques, for example, to look at the chemistry of the structure. And additionally, we can also do in situ if we use the contacts in the TEM microscope. So we make these membrane chips in the clean room in Institut Nel Nanofab, starting with a 4-inch wafer. where we have silicon nitride layers on both sides of the wafer. And then with the combination of optical lithography and etching, we pattern the silicon nitride wafer. And then by putting it into a KOH bath, silicon is etched along the 111 planes and until it hits the other silicon nitride layer. And this is then our membrane. And between the chips, we also etch these little V grooves, allowing us to separate the chips from one another after fabrication. So then we have our membrane, planar or with holes. We put a nanowire and by dispersion typically. And then with electron beam lithography, we write electrical contacts to this nanowire. So because we make the membranes on a wafer scale, we can then do this lithography on an array of membranes still attached. And this is just facilitating the processing. And once we're happy, we can cleave out one chip. And this chip is then inserted into our TEM in-situ holder that you see here. And here is the zoom on the tip region. And here we then make contact with the chip with these 6 needles landing on large contact pads. And now we are ready for an in-situ biasing experiment. So if you find this interesting, we recently published this nanotechnology paper giving many details about the membrane fabrication and a summary of all the things you can do with them, or we did with them. So most of the experiments that I will show you in the first 2 parts of the talk are done with scanning transmission electron microscopy. And these experiments were mainly all carried out in the TEMs in CA Grenoble in the nano characterization platform inside the IRIG lemma group. And here we have a focused electron beam that is raster scanning over our sample point by point. And at each point of the scan, we can collect a signal on some detector. For example, we can collect the transmitted disk, or we can collect electrons that are diffused over larger angles or scattered on this so-called high-angle annular dark field detector. And this is quite interesting because a heavier element scatters more electrons, so we get a qualitative chemical signal that is quite, quite easily interpretable. We can combine this also with collecting X-rays emitted at that location to get chemical information about the signal. So the first study I'd like to show you is already a bit old. So this is a correlated study on a gallium nitride, aluminum nitride nanowire heterostructure. And mainly we were looking at the influence of the polarity. So I first have to explain you what the polarity is. So these semiconductors, they crystallize in the word side crystal structure. It looks like this along a 0, 2 to 1 direction. So here we have the C direction. And because the total charge of all positive gallium columns doesn't completely superpose on the total charge of all negative nitrogen columns, we have here this little dipole at the interface. But in the crystal, this is screened. But if we have an interface, for example, if we make gallium nitride, aluminum nitride, and then gallium nitride, at the interface, this dipole is not compensated. So then we get, depending on the direction of the polarity, we get either negative or positive charges, leading to this very, contrasted or very accidented conduction band profile. So the polarity in these materials is very important to understand the field distribution in the structure. And I should add that these are wide bandgap materials. So here is the experiment we did. Here we have the nanowire. It's gallium nitride. It has a single aluminum nitride barrier. And here you see the metal electric contact. So it's on this membrane. This is the structure of the gallium nitride crystal that you can then compare with this average high angle annular dark field image here. So these bright dots are the gallium columns. They're quite heavy. And in the high angle annular dark field, we can directly see the position of the nitrogen columns. However, if we make a profile here along this line, we can see that here is a small bump, while here is a dip in the intensity. So this allows us then to position the nitrogen columns, and this shows that our C-plane is terminated with nitrogen atoms, like in the schematic, and this is then commonly referred to as 0, 0, 0, -1 n-polar nanowire growth direction, because the nanowire went to the left on my screen. Now, this is nice, but maybe more interestingly, we could also look at the behavior of this nanowire to understand what the polarity does to its electrical properties. So for example, we measured current voltage characteristics of this nanowire, but also of some others. Here you see 3, where we also had the TEM images. As I said, in the center of the wire, we have this aluminum nitride insertion, which is a very high band gap. So it's basically wood. The current has much difficulty going through. But around this, we have a gallium nitride shell. And so it was likely that current would prefer to flow through this shell. And we could confirm this doing a finite element simulations of the potential of the conduction band profile here in the shell region, which is what you see here. Due to the combined effects of the polarity and strain, we get something looking like a p-n junction. And this explains why our current voltage measurements have this clear forward bias. Additionally, the amount of current we get through the device scales very well with the thickness of this gallium nitride shell. So we could clearly show that the current flows through the shell and understand the shape of these current voltage measurements. So this was already the summary of this first part. I wanted to keep it fairly short. So in this work, we showed that the nanowires grow in the n-polar 0, 0, 0, -1 direction. And we can clearly measure the influence of the polarity on its properties. And we also saw this in other papers, but this was this nanoletters from 2012. And clearly the properties of the contacted nanowires are easier to understand if you have the TEM image of the same nanowire. And it also greatly helps with the modeling of that object. So now I would like to come to the second part of the talk, and this is making aluminium contacts on germanium nanowires using in-situ metal propagation. So we will look at the reaction, the chemical composition of the reacted product, the kinetics of the reaction, and finally that we can fabricate a small germanium quantum dot or disk in such a structure. And this work was started in the PhD of Khalil, and then mainly done in the PhD of Min-An Leong in collaboration with colleagues from CEA and Technical University of Vienna. So in literature, it was clearly realized that such a metal propagation in a nanowire is quite an interesting system because, for example, we can find this paper here with nickel and silicon, and this is also nickel silicon. So here you see the nickel going in, and if you can stop this reaction at the moment you want, then you keep this little segment of semiconductor between metallic contacts with very well-defined and clean interfaces. And you can find many papers in literature, mainly silicon and nickel, or germanium and nickel, but also with platinum in silicon. So here you see very nice, well-defined silicon region, or indium in zinc oxide nanowires. In all these papers, a intermetallic phase is created. So it's not a pure metal. And this is different from the system I will show you in the following, germanium and aluminium. Last part, I have to tell you about how we carry out these in-situ experiments. So we are looking at this metal propagation in germanium nanowires using Joule heating, and we can carry out the experiment in different ways. We can use this kind of calibrated heater chip from dense solutions. Here again, you have the silicon nitride membrane, and inside the membrane, there is a buried heating spiral. And we have 2 contacts to drive the current and 2 to measure the potential. And so here, this whole zone is heated, and between the spiral, we have these small windows with the thin nitride where we can put our nanowire and put some contact material or metal reservoir. And this is well calibrated in temperature. Another possibility is to use our homemade chips, where we also have a nitride membrane. We can disperse a nanowire and then contact it with electron beam lithography to write these strips on the wire, each going to their own contact pad. And then when we flow a current through the strip, again, by Joule heating, it's heating up and starting the solid state reaction. So the advantage of this approach is that it's easily combined with electrical measurements. And the disadvantage is that these are not temperature calibrated. So we just have a potential or current we apply, but it's not directly possible to convert it to temperature. Okay, so let's go to the first experiment. So here you see two germanium wires side by side underneath an aluminium strip line, where we then flow a current to initiate this reaction. And you will see that doing this, the contrast starts to change inside the nanowire, and a much darker contrast starts to propagate, replacing this bright contrast. So I remind you that germanium is more heavy than aluminium. So this bright was the original germanium wire. And then something related to likely lots of aluminium is going into the wire. Once all the material underneath the strip is consumed, you see that this reaction proceeds symmetrically from out underneath the strip, and that the interface is really very, very sharp and well defined. So we have performed many of such experiments, and the first thing that we did already a long time ago, we wanted to look at the chemical composition of the created segment that's likely rich in aluminium. So we used EDX mapping, energy dispersive X-ray spectroscopy. Here you see such an EDX map. This is the converted region, and here we then make a profile over the nanowire that we integrate along quite a big zone. This map is quantified, and the profile is then compared with a 3D model of the nanowire. This approach was developed by Eric Robin, and it was first published in this paper in 2016. And what we see is that we obtain a best fit between the experimental profile and the model using a nanowire with a hexagonal cross-section. And then we find that we have a core of pure aluminium surrounded by a shell of aluminum oxide. And on both sides of this shell, we have a layer that is maybe even pure germanium. So in fact, what we have made here is a core shell structure, pure aluminum core, and then here you have this germanium-rich layer and aluminum oxide shell. We also did experiments looking at the reaction kinetics, and we then looked at the position of this reaction interface as a function of time. So this is what we call L as a function of time. So here you see two different experiments, one carried out at a known temperature, one carried out at some potential. Well, it's probably similar, but we don't know the exact temperature. And what we see systematically in these experiments is that this kind of curve, they have this kind of parabolic behavior, and they can be fit with this equation, which is a very classical diffusion equation. So L can be expressed as the square root of the diffusion constant and time. But we didn't see a clear influence of the nanowire diameter on the speed of the propagation. So sometimes the smaller one would be faster, but sometimes the bigger one would be faster. And according to models in literature, these two observations indicate that this reaction is limited by some volume diffusion process, so not surface influence. We have also done similar kinetic studies in nanowires now with large diameters. Oh, sorry, I think I forgot to mention this was done in thin nanowire diameters. Thin meaning between like 20, 50 nanometers. And this is a study in larger nanowire diameters, say 100 nanometers or above. And interestingly, we do not see the same kinetic result in thick nanowire. So here, the length the interface has traveled over time is much more linear with some jumps. And again, according to models, this may indicate that the reaction is limited by some interface, and we speculate it's this reaction interface. And I will show you now why we think it is the reaction interface. So here you see, again, an experiment in such a thick nanowire, where you see how the reaction proceeds in small nanometer-sized jumps, and then it flows over the interface. So this is the remaining germanium wire. This is the converted aluminium section. And here we have some roughness at the nanowire surface, and then boom, we get a relatively larger jump at these regions. Here, the nanowire was the S-grown germanium nanowire. So on the surface, we had the native germanium oxide, which is, as you may know, not a very good oxide, because this is why germanium basically didn't make it in industry. And this kind of jumps in the propagation, they are a problem if you want to deterministically make a semiconductor region of well-defined size, because then you go, and then boom, it's gone. So it's not good. You need to control it. So then what Min An did, and what the colleagues in Austria had already tested ex-situ, he put this aluminium oxide shell around the germanium wire before having removed the native germanium oxide, and then he did this experiment. So on this side, it is already propagated, and now he's heating from this side, which is outside of the field of view. So this is the remaining germanium segment. And this is a fairly wide nanowire. It's 150 nanometers or 140 nanometers in diameter. And you see that now the propagation is much smoother, and we have gotten rid of these jumps. And in this way, it's possible to deterministically in situ fabricate a germanium quantum disk, in this case, or quantum dot of a defined size. So in this case, I mean, Annie made a disk of 7 nanometers, which I think is really nice. Okay, so to wrap up this second part, I've shown you that we have studied, that we have observed in thin nanowires, the reaction is limited by aluminium volume diffusion, as we have not observed this size dependency. In thick nanowires, the reaction appears limited by the reaction interface, where the interface can remain like trapped at surface defects. Then we think that the diffusion occurs like this. So here, look please at this image. So this is the remaining germanium part and the converted region. So aluminium arrives by volume diffusion to this interface, while germanium goes in a surface channel and going back to the aluminium reservoir, where it then incorporates at surfaces or grain boundaries. And we think that this germanium layer we detected here around the pure aluminium core is in fact this germanium going back. And we could also detect germanium here in the aluminium metal strip. Finally, surface passivation improves the control of the interface, so it then is possible to make a small quantum dot of deterministic size. And these works was published in these 2 ACS papers. So now I would like to come to the last part of the talk. So, well, I hope that you're still awake. Here, I'm showing you a study where we look at the Schottky contact on a zinc oxide nanowire using a combination of in-situ biasing and holography. So first I want to explain you what electron holography is. So here it's a TEM technique now, not STEM. So we have parallel electron beam, and we put the sample in part of the beam, and the other part of the beam goes through vacuum. Then, with the help of a charged wire called the biprism, these 2 waves are interfered, and you obtain an electron hologram or interference pattern in the image plane. the interesting point is that from this interference pattern, we can reconstruct both amplitude and phase images of our object. Well, in normal TEM, without doing anything fancy, you only obtain an amplitude image. But it's quite interesting to look at the phase, because the phase is influenced both by magnetic fields and by electrostatic fields. And so in the absence of magnetic fields, we can relate the change in phase with this equation where we have a constant and then an integral along the beam, and then we find the projected electrostatic potential. And we can tentatively separate the electrostatic potential in these two terms. First, we have something related to the atoms in our sample, because they will also dephase the electron wave. So we can think of this as the chemistry. It's typically referred to as main inner potential. And on top of that, we have something that describes electrostatic potential due to doping and surface charge and so on. The problem with electron holography is that it's difficult to do quantitatively, because we can have other influences on the phase. For example, if we have chemical contrast, then this can give us some gradient in our potential term. If we have diffraction contrast, it can also influence the phase, and not necessarily the entire sample thickness is electrically active, for example, due to surface depletion or inactive surface layers. However, we need to know the thickness here. So if we put, and this should be the electrically active thickness, but we don't know if the whole thickness is electrically active. So a solution to this problem is to use in-situ biasing, because then we can subtract some reference image, typically zero bias image, to remove all signal but the varying electrostatic potential. And this has been realized in literature very long time ago. And well, we're still working on it because it's still interesting. So here is some of the key papers, I think, of in-situ biasing and holography. So the main objects that have been studied are in bulk specimens, p-n junctions. For example, in this paper by Twitchett, they could see that the potential step is increasing as a function of applied reverse bias. And from this, they can both extract the built-in potential at the junction and also the electrically active thickness. In nanowires, there's not so many papers. We have this paper by Hay et al., where they made the contact to the nanowire with like a moving probe. And basically, they observed that it's very difficult to make a good contact here to be able to polarize this p-n junction. And in Denmark, they also succeeded to measure the resistivity of a gallium nitride nanowire in this case. So in the topic I want to show you today is about a Schottky contact. So we're looking at the Schottky contact on a zinc oxide nanowire. I will rapidly remind you what it is. So if we have a metal and a semiconductor far away, the vacuum level is continuous. And then if we bring them into contact, we have two conditions. The Fermi level needs to be continuous and the Fermi level needs to line up and the vacuum needs to be continuous. And these two conditions then force valence and conduction bands to bend either up or down at the interface. And therefore we get this region that is void of any mobile charges, the so-called depletion region. So what we're trying in the holography experiment to more and more increase reverse bias, increase the depletion length, and this is what we want to see. So the reason we started on zinc oxide nanowires is that my colleagues, Julien Pernot and Fabrice Donatini, they had performed many experiments on such structures using cathode luminescence. And systematically, the depletion length was not well understood. So here is a structure we will later see in the TEM experiments, but they have done these experiments on many nanowires. So this is the zinc oxide nanowire. The contact we will bias, and it's connected to a ground by these crossing nanowires. Here you see SEM image, and this is a cathode luminescence image at zero bias. So this dark contrast means that if the electron beam hits here and here and here, light is emitted and collected. Then if we apply a negative bias, here this region becomes white. So we have propagated the depletion region. Now there is a field. And when the electron beam creates an electron hole pair, is then separated by the field. So they cannot recombine radiatively, so no light. Then making a profile on such an image, it's possible to extract the depletion width as a function of bias, and systematically they got such a linear extension, and you cannot explain it with bulk equations or finite element simulation. So this was a question mark, and we thought, okay, let's try electron holography. So this is the same wire. Here you see a hologram made at 80 kilovolt, and then from this hologram, we can calculate the phase image. And what we did is that at this contact here, we applied different bias values going from 0 to -15. And again, reconstructing the phase image. And for each biased image, we then subtract the zero bias hologram, the zero bias phase image, right? This is what I explained at the start of this section. So the idea is that subtracting the zero bias phase image, we remove all contrast but the varying electrostatic potential. This is also a difference image between zero bias at the start and zero bias at the end of the experiment. You see that the signal is fairly small, much smaller than here. It goes to 10 radians, here 0.4, just to validate that the object is not being electrically modified during the experiment. So then we make profiles from the contact into the nanowire, and this is what you see here. So for an increasingly negative applied potential, the phase is going down more and more at the contact and penetrating further and further into the nanowire. And this is in fact the depletion width that we can directly visualize. So you can see at a bias of -7 volt, we have roughly a depletion length of 200 nanometers. And at -15 volt, it extends to roughly 300 nanometers. So we can measure these depletion lengths. We then wanted to compare this with finite element simulations that we have done with NextNano in 3D. So we made a similar structure with a nanowire under Schottky contact, and we played with two variables, different end-doping concentrations of the nanowire and different values of negative surface charge, because they can both influence the depletion length. And this we have then projected like in the holography experiment. So this is basically the result, the comparison of experimental depletion width and simulation. So the colored symbols are the results of simulations, and these black symbols here are the experimental holography data. Here the depletion length is plotted as a square. The experimental data are fitted with this equation that describes the depletion width in a bulk system. So you can see that in our nanowire, the depletion length behaves as a bulk system. So the nanowire, there's no nano size fancy stuff. It's like bulk. And so we use different end-doping concentration and different surface charge. And you see that these green symbols give a fairly good representation of our experimental data, or agree fairly well with the experimental data. And they would imply that we have a doping in the order of 10 to the 18 atoms per centimeter cube and a negative surface charge of -2.5 10 to the 12 charges per centimeter square. And now we have a problem because the depletion length is influenced both by doping and by surface charge. So it's not a unique solution. But it does so happen that this combination of the two agrees well with literature and independent measurements of these quantities, for example, with electrical measurement or optics. Here, this is the same data where the depletion width is plotted in now linear scale, the holography data, and compared with the catoluminescence result on the same object. And you see that we really observe different tendencies of these values, but even on the same object. And I think this is important to keep in mind. And our conclusion is that holography is more sensitive to the nanowire core, while SEM techniques are more surface sensitive. So to wrap up this last part, this nanowire has a doping around 10 to the 18 atoms per centimeter cube, which is compatible with the metallic nanowire. We find a surface charge of minus 2.5 10 to the 12 charges per centimeter square, which is compatible with this paper in nanotechnology. And in this nanowire, it gives us a depleted surface region of around 36 nanometers, which leaves an active thickness of 70 to 80 nanometers. And these values are compatible with optical measurements in literature and also with the strength of our phase signal. And yes, holography did give us different values for depletion than SEM techniques. So this was published in this nanotechnology paper. So finally, I would like to thank all my collaborators and mainly the PhD students, Min An, Luang, Maria, and Khalil. And would like to thank the facility. So, you know, I think that Grenoble is here, surrounded by the Alps. And here we have the site of CNRS and CEA. So here's Institute NEEL. There's nanowire activity on 2.5 and 3.5 and 2.6 nanowires in the nanophysics and semiconductors group. And also here for silicon and germanium in the Synapse team. And here we also find the nano characterization platform where we have this wonderful TEM equipment. So as a wrap up, I showed you correlated experiments, aluminium exchange reaction in germanium nanowires, and that we can visualize the depletion with using electron holography. So I hope that you thought that TEM biasing is interesting. In-situ biasing in the TEM is interesting. I would like to thank the ANR and the ERC. So indeed, we are working on this visualizing charges, but that is ongoing. So maybe I can present that to you in 4 years, I hope. So I would like to thank the funding agencies. And finally, like to draw your attention that I am part of the organization committee of the quantitative electron microscopy school that will hopefully take place in May in 2021 in the south of France. So I thought if there is PhD students or postdocs or researchers wanting to deepen their knowledge in TEM, this is really a very nice place. So don't hesitate to check the website or ask me questions directly. And I'm open for questions, or I hope that yeah, you have questions. Thank you for the invitation.
Thank you very much.